This is the fourth lecture on linear harmonic oscillator. Let me first recapitulate what we have done in the earlier class. In the earlier class, we found that the normalized Hermite-Weber function is this, and which in Dirac notation can be written as Kn. Then the recurrence relation involving Qn is this. This is written, both the relations are written in bracket notation. This is the recurrence relation for Q prime of n. Now we consider the corresponding complex conjugate relation. When we take the complex conjugation of this is actually a column matrix, then we will have a row matrix, and the row matrix is denoted by the and the corresponding complex conjugate relation of these two are written here. You see that since we have originally the operator Q times n, when we take the Hermitian conjugate of it, then we will have n times Q dagger. Since Q dagger is Hermitian, this is equal to nq. This is the relation. And so this is a number, so we will have bra n minus 1. This is this, and then for this. For conjugate relation, we have used M notation, M quantum number, and for the Ket relation, we have used the N quantum number. Now, just in the last class, we have worked out the expectation matrix element for this. So we change, this is just a recapitulation, we change this part by this relation, so we get m, and this square root is there, then when we take the inner product of this leads to a delta function. We state that this is the single de-excitation, and this is single excitation process. So we summarize the result that we are getting from this. So we write, this will be required in the subsequent discussion, so we preserve this. This is one set of results. Now we want to calculate the matrix element for Q square. Now our next is to find out the matrix element. We divide this into two parts. We write it as this: M Q dagger, which is equal to Q times Q n. So for this we use this relation and for this we shall use this relation. So we have 2 1 by root 2, which is half. Half, then we will have for this this is written for this part, and for the rest part so the result is when this is multiplied by this, we have half, it is common all through, m in scalar factor comes out, and then we will have m minus 1 n minus 1. This is the dot product or inner product between these two. Then this is multiplied by this. Integration is implied. Then this term is multiplied by this. And finally this is multiplied by this. Now we see that this leads to a delta function. These are related to the delta function, so half. Then from this term we will have now we see that this term contributes when m plus n is equal to this. So this contributes when m is equal to n. So is this term when m is equal to n. This term contributes when m is equal to n plus 2, and this term contributes when m is equal to n minus 2. So if we have a system initially in a state m, then these two processes represents that m, the state is unaltered, the state remains unaltered, that is the quantum number of the system is not changing. This is called elastic process. This definition of elastic process is something different. Elastic process, so this is also the elastic process. Elastic process means the internal state of the system is not changing, that is the wave function remains the same. In this case, the system was, if we assume the system was initially in a state n, then it goes to a state m where m is 2 steps ahead. So this is double excitation process. And this is obviously double de-excitation process. So we will have these different cases. Now we can summarize the result like this. In this case, we replace m by this, and there is a half factor all along, keep it in mind. So this is m will be replaced by this. So this is n plus 1 into n plus 2 square root when m is equal to n plus 2. For an elastic process, this is n, this is n plus 1. So altogether this is 2n plus 1 when m is equal to n. And lastly, this process, for it is n into n minus 1 within square root, and when m is equal to n minus 2 and 0 otherwise. So if we consider the interaction to be proportional to q square, that is the distance square, then the system can can retain its state, that is, it may be in the same state as it were before the interaction, or it can go 2 steps up. But follow, this is the double excitation, in which case the system engulfs 2 photons of each of energy h nu, and in this case system releases 2 photons of each of energy h nu. I will come to the transition or selection rule in a later class. Now I come to the calculation of matrix element corresponding to the momentum operator. We know that momentum operator, P operator, is equal to minus IH cross del del x. If we transform this into the dimensionless form, then it is IH cross alpha ddq, because we used q is equal to alpha x. So the momentum operator, this thing we are keeping in hand, and we write that m ddq operating on state n. So for m we write the, and for this part we replace it by this relation, this recurrence relation. So keep this factor in mind. N plus 1. So we write the matrix element like this. first one this. Now we go to the calculation of p square element. We again, as before, divide it into two parts and we write it as ddq and for the Kt equation we use this, and for the Bra equation we use this. So this is 1 upon 2. This is this part, and from this part we have so if we multiply these terms we will get, when this is multiplied by this, the numerical factor is m into n and the delta function involved is m minus 1 n minus 1. Then this is multiplied with this. This is multiplied with this. And finally the last term. You see, these are the elastic processes. These two are elastic processes. This represents m is equal to n. This also represents m is equal to m is equal to n. This term represents m is equal to n plus 2, and this term represents m is equal to n minus 2. So these two are the elastic processes. This is double excitation, this is double de-excitation process. So we again write the summary. Half is there, and it is n plus 1 n plus 2 under square root. M is equal to n plus 2. Then this is again, this is n, this is n plus 1, so 2n plus 1 when m is equal to n, and for this case n into n minus 1. and 0 otherwise. This is all the matrix element that we have calculated, and now come to the expectation value of position. We know that Q is equal to alpha x, that is x is equal to Q by alpha. So if we expectation values, the expectation value of x operator in a state n is defined as n x operator n. Writing in longhand, it represents x n is equal to psi star x psi dx over all x. This is this. So we see that it is 1 upon q times, this is 1 upon alpha times n q operator n, and as per this relation it is 0. So we find that the expectation value of position of the harmonic oscillator is 0. It is indeed because the oscillator oscillates symmetrically about the equilibrium point. So when we take the average value of the position, it will give you 0 value. Now come to the expectation value of x square operator. This is 1 upon alpha square n q operator square n, and we find from here, from this relation, that it is n plus half. Alpha square. Similarly, if we want to find out the expectation value of P operator in a state, this is minus IH cross alpha. So let me first write the definition. Writing in longhand, it is psi star minus IH cross D. For one dimensional case, it is ddx psi n dx. This is the compact form. The bracket notation is this. So we write it as minus IH cross alpha in ddq n, and we find that this is 0. So this is 0. And finally we calculate the expectation value of P square operator in a state n. This is n P square operator n. So this is, from this state we will have plus IH cross alpha, and from the other it is minus IH cross alpha. This is H cross square alpha square. This is alpha square, and this part we find it that it is n plus half. So let me again summarize these things. we will write all these things. So the expectation value of x operator in a state is 0. Expectation value of p operator in a state n is 0. Expectation value of x operator in a state n is expectation value of n plus half by alpha square, and expectation value of this is square, I have missed this, x square operator is this, and expectation value of p square operator in a state n is finally h line square alpha square n plus half. This is what we have done till now. Now if we want to have a physical description or physical meaning of it, you see that the harmonic oscillator, the expectation value of p operator is 0, because it is equally likely for the harmonic oscillator to move to the right as well as to move to the left, so its expectation or average value is 0. Now we come to definition of uncertainty. For uncertainty, we define of a variable O as this: delta O, this is the uncertainty square, is equal to expectation value of O operator square in a state this minus this is just the standard deviation, definition of standard deviation. Sorry, this the standard deviation in x, standard deviation in x is defined as x square average minus x average square. This is the, in terms of in quantum mechanics, these averages are replaced by expectation values. This definition actually comes from the definition that sigma x, this is sigma x square. Sigma x square is 1 by n summation over x average minus xi whole square, I is equal to 1 to n. This definition leads to this, which is very obvious to you. So the expectation value in, or the uncertainty in position delta x n square, this is equal to the delta x n square, or no, keep it n over here, so this is x square in a state n minus, this is 0, and this is, we have this value as thus. So this is similarly delta pn square is equal to p square average in a state n minus this is again 0, so we have this line. So the product uncertainty is delta x n delta p n is equal to these two multiplied by multiplying these two and then taking the square root. Alpha cancels out, so this is each line n plus half. We see that the minimum uncertainty is obtained when n is equal to 0 and it is h cross by 2. So the minimum on this is the uncertainty relation, and delta x in the state 0, delta p in the state 0 is h cross by 2, the uncertainty relation, and other uncertainties are greater than this. Now we come to the expectation values of the energies. The potential energy of the harmonic oscillator is governed by potential energy of the harmonic oscillator is given by V of x is equal to half m omega square x square. So the expectation value of potential energy in a state n is this multiplied by x square average. So it is half m omega square times alpha square. Remember the value of alpha. Alpha is equal to, alpha square is equal to m omega by h cross. So this is half times h cross so one m cancels and this result becomes half h cross omega. Similarly, the kinetic energy T is equal to half P square by twice m. So the expectation value of this operator is and we write for P square h line square alpha square h line square alpha square by 2m n plus 1, and this is h line square by 2m for alpha square is m omega by h line n plus half. On cancellation, so we see that the expectation value of kinetic energy and potential energy are the same. So this result is also obtained in the case of classical oscillator, and the expectation value of energy in a state, this is the expectation value of the kinetic energy in the state n plus expectation value of the potential energy in the state n. So as both of them are same, so this is n plus half h cross omega. The minimum energy is obtained from n is equal to 0, and this is the 0 point energy. So we see that the 0 point energy actually is a manifestation of uncertainty principle. In a later class we shall use another way of convincing that the 0 point energy is a manifestation of the uncertainty principle.